Welcome to the third module in this introductory series on FMCW radars. This video is going to be a deep dive into velocity estimation. And like in the case of range estimation in the first module, we are going to be looking at things such as the maximum measurable velocity and the velocity resolution. So the kind of questions that we're going to try and answer in this module are, you have a radar and you have an object in front of the radar. How does the radar estimate the velocity of this object? And this is going to be a recap from what we've learned and what we've seen in module 2. What if there are multiple objects, perhaps at the same range from the radar, but with different relative velocities? How close can the velocities of two equi-range objects get and still be resolved by the radar? Is there a limit on the maximum measurable velocity in a radar? Like in the earlier modules, we are going to start with a quick recap of some Fourier transform concepts. So far, we've been talking about Fourier transforms on a continuous time signal. Similar concepts are also valid for discrete signals. So here you have a discrete signal consisting of a phasor rotating at a constant rate of omega radians per sample. So between any two samples, this phasor has rotated by omega. So we will use the term discrete angular frequency or sometimes just frequency to refer to this omega. Note that each of these phasors actually represents a complex number. So another equivalent representation of the sequence would be this particular mathematical representation that you see here. A Fourier transform, or a discrete Fourier transform to be exact, of the sequence would result in a single peak in the frequency domain at the discrete frequency omega 1. And here I show this word FFT, which is just an efficient algorithm for computing this discrete Fourier transform. Now, if this discrete sequence consisted of two phasors instead of one, as shown here, where you have the blue phasor rotating at a discrete angular frequency of say omega 1 and the red phasor rotating at a discrete angular frequency of say omega 2, the Fourier transform of this discrete sequence would actually have two peaks at discrete frequencies of omega 1 and omega 2 respectively. How far apart do two frequencies, omega 1 and omega 2, have to be for them to show up as separate peaks in the Fourier transforms? So here you have two phasors rotating with slightly different frequencies of omega 1 and omega 2, such that over n samples, the second phasor has traversed a half a cycle or pi radians more than the first phasor. So in this example, omega 1 is 0, omega 2 is pi by n. So over n samples, the cumulative angle of omega 2 with respect to omega 1 will be pi radians or half a cycle. And as you can see here, that is clearly not sufficient to resolve these two objects in the frequency domain. Here you have the same two phasors, but now observed over a longer time period. We now have 2n samples instead of n samples previously. Over these 2n samples, the second phasor has traversed a full additional cycle compared to the first phasor. And as you can see, the two frequencies are now clearly resolved in the Fourier in the frequency domain. So the takeaway here is, longer the sequence length, better the resolution. And in general, a sequence of length n can separate angular frequencies that are separated by more than 2 pi by n radians per sample. Let's take a moment to compare the resolution criteria for discrete and continuous signals. Recall from the last module that for a continuous signal, two frequencies can be resolved as long as their separation delta f is more than 1 by t hertz or 1 by t cycles per second, t being the observation window. For discrete signals, as we stated in the last slide, two discrete frequencies can be resolved as long as their separation delta omega is more than 2 pi by n radians per sample. So note the unit here, radians per sample. which is actually the same as 1 by n cycles per sample, since each cycle is 2 pi by n radians. So now if you look at these two equations, the correspondence between the discrete and the continuous case really comes through. In one case, the resolution is inversely proportional to the length expressed in the observation time t, and in the other case to the length expressed in the number of observed samples n. So I think we now have all the tools to understand how an FMCW radar can measure velocity. The basic idea is the following. You transmit two chirps separated by a time of Tc. The range FFTs corresponding to each of these chirps will have peaks in the same location but with differing phase. The measured phase difference omega between between the phases of these two peaks will directly correspond to the motion of the object. And note that if the velocity of the object is v, the object would have moved a distance vtc during this time period tc. So this is the equation here where the phase difference between the phases of the peaks corresponding to these two transmitted chirps is given by 4 pi times the distance that the object has moved during that period divided by lambda. And then rearranging this equation, you can directly estimate the velocity from this measured phase difference. So the takeaway here is that the phase difference measured across two consecutive chirps can be used to estimate the velocity of the object. Is there a limit on the maximum velocity that can be measured using the technique that we just described? Note that the method relies on a phase difference measurement, which is unambiguous only as long as this difference is within plus or minus 180 degrees or plus or minus pi radians. This is illustrated in these series of figures here. For example, if we visualize the phasor motion across two chirps, for positive velocities, you could visualize the phasor moving anti-clockwise. Likewise, for negative velocities, you could visualize the phasor moving clockwise. Now, if the movement in the clockwise or anti-clockwise direction is more than 180 degrees, there would be an ambiguity. For example, in this illustration, one cannot conclude if the phasor moved by an angle A in the anti-clockwise direction or an angle B in the clockwise direction. So, unambiguous measurement of velocity requires that the phase change across the two chirps is less than pi, which means we have this expression for the phase change from the previous material. This expression must be less than pi, which means that which gives you an expression for the maximum unambiguous velocity that can be measured. So the takeaway here is that the maximum relative velocity that can be measured by two chirps spaced Tc apart is given by this expression. So you can see here that a higher Vmax requires that the chirps be closely spaced. So we've just seen how one can measure the velocity of a single object in front of the radar. And I hope it's clear that the same method can be applied for multiple objects in front of the radar as long as they are at different ranges from the radar. But what about if there are multiple objects at the same range from the radar? So in this example here, you have two objects in front of the radar which are at the same range from the radar but have different velocities v1 and v2 relative to the radar. So as we discussed earlier, there is going to be a single peak in the range FFT, corresponding to these two chirps that I would transmit. But the phasor at that peak is going to have components from both objects. So the simple phase comparison technique that we described earlier will not work. The reason being that the phases here have components from the velocities of both these objects. So what would be the solution? One solution is to transmit a series of equispaced chirps instead of just two chirps. And so here you have n equispaced chirps. And building on our earlier discussion, the range FFTs corresponding to each of these chirps would have peaks at identical locations, but the discrete sequence corresponding to the phasors of these peaks would have two rotating phasors rotating at frequencies of, say, omega 1 and omega 2, corresponding to the two velocities v1 and v2. So an FFT on this discrete sequence would then show two peaks corresponding to discrete angular frequencies of omega 1 and omega 2 respectively. And then, having measured omega 1 and omega 2, you can then back calculate the velocities using these expressions that we've seen before. Before we move on, let's clarify a few terms. So this FFT here, which is done across the chirps, is typically called a Doppler FFT in literature. And this sequence of equispaced chirps over which the Doppler FFT is being performed is called a frame. So the basic unit of an FMCW radar, the basic transmission unit of an FMCW radar is really this frame. What is the velocity resolution capability of the Doppler FFT? That is, what is the minimum separation between V1 and V2 for them to show up as two peaks in the Doppler FFT? It turns out that deriving an expression for the velocity resolution is quite simple and analogous to what we did in Module 1 for range resolution. All we need to do is use these two facts that we know, and at this point I would urge you to pause the video and try and derive this expression for velocity resolution yourself. So two objects whose velocities are separated by delta V will have their angular frequencies separated by a delta omega given by this expression over here, where Tc is the separation between adjacent chirps. And from the properties of discrete Fourier transforms, we know that two frequencies can be resolved as long as their separation delta omega is more than 2 pi by n. So now substituting this expression over here and rearranging this a little bit, we get this following inequality which gives us an expression for the velocity resolution. And note that this expression here, n, the number of chirps, times the duration between adjacent chirps is actually equal to the total frame time. So finally we get this expression for the velocity resolution, which basically says that the velocity resolution of the radar is inversely proportional to the frame time and is given by lambda by twice the frame time. Time for a question now. These two frames have the same length, frame length TF, but the frame corresponding to radar A has twice the number of chirps compared to the frame corresponding to radar B. The question is, what can you say about the maximum measurable velocity and the velocity resolution of these two frames? This brings us to the end of the third module. In the next module, we are going to use all that we've learned so far with respect to range and velocity estimation to design a transmit signal which meets certain specified requirements.